Well, it looks like it's time. Welcome back once again, folks. So for our work today, we're going to start to take on the sometimes infamous section 3.5 on implicit differentiation. This one is a bit notorious in the sense that sometimes it's kind of hard to see exactly how the differentiation techniques are working in this section. So we're going to take our time with this one, as much time as needed, to show on an initial example two ways of differentiating, one way explicitly, like we've been doing all along, and then start using the implicit differentiation method. And before we get very far in that section, we'll see the power of using that method. The idea with implicit differentiation is essentially just the chain rule. So we're going to be reviewing the chain rule really a lot ever since we introduced it in the last section, 3.4. And then we'll see another big technique for implicit differentiation when we go to derive the next classification of functions, the logarithmic ones. We already know how to differentiate the exponential functions, but their inverses are all the logarithms. And that's where this implicit differentiation works. To show how to differentiate an implicit function, or excuse me, an inverse function, like say a natural logarithm, or even a sine inverse or cotangent inverse, implicit differentiation is the main technique. So we'll show how that works in section 3.6 as well. Start off with implicit differentiation, leading on to looking into logarithmic functions. Any questions or comments at all, folks, before we give it a start? Okay, well, let's jump in. So again, the major idea is the chain rule. So we'll review that as we're going through the notes. And here's how our first example starts. Really, we're going to do the same problem twice, the exact same problem. That's a weird thing to do sometimes in a math class. But for here, this new technique, implicit differentiation, it makes sense. Part A is going to be the fundamental thing we've been kind of doing all along, differentiating as normal. Here we want the slope of a tangent line, just the slope. We don't want the tangent line equation. Then we're going to do it all over again, but we'll be using implicit differentiation, our brand new technique, to show how it goes. This way, by solving a problem twice, we're going to be able to see just how this all works and how chain rule gets involved with implicit differentiation as well. So let's start off on example 1, part A, using nothing but first principles to kind of set up the analogy for part B. We have an equation, y squared equals 5x power 4 minus x squared. We want the slope of the tangent line at the point 1, 2. And the immediate red flag here is, notice how weird that looks. It's y squared equals 5x power 4 minus x squared. Y is not explicit as a function of x until y is completely solved. So when we see this, because of the y squared on the far left, there are two implicit functions of x. Now, we only need one function to get this started. We need one function whose graph is going to pass through the point 1, 2, and then we can differentiate it, get the slope of the tangent line. So the way this should start is, let's just find that one function. You can take y squared equals 5x power 4 minus x squared, and just solve for the variable y by taking the square root. You would then obtain y equals, but in an algebraic setting, when you take the square root, we have two possibilities. It's either the positive or negative root of 5x power 4 minus x squared. So there are our two implicit functions. Well, you need just one of them. If it goes to the point 1, 2, it's probably the positive root that we're going to take. Let's throw this on the graph just to get a view for what we're looking at here. We have one function, y equals, I'll put in the positive root, square root, 5x power 4, minus x squared. So there's our first function. Notice it has an interesting domain issue. It's undefined for values between -1 or wherever that value is, -0.45 and positive 0.45 approximately. Here's our next function, y equals, we bring in the negative square root, 5x power 4, and I forgot the negative sign, let's throw that in, minus x squared, and that's the other part. So this curve, both the red part and the blue part all together, is just this original curve right here, y squared equals 5x power 4 minus x squared. It's not a curve of one single function because, oh, observe, it fails the vertical line test. Just immediately and spectacularly, any vertical line to the right of about 0.47 will fail the vertical line test, hit the curve twice. That's why we have two implicit functions. We have a positive root, we have a negative root. We're concerned about the 0.12, and that occurs on the function that involves the positive root. The first function, the one in red. That means we're going to pull out the positive root and just work from that one. So we can say y equals root 5x power 4 minus x squared. Since that's the function that actually goes to the point 1, 2. If we didn't have that further information, we couldn't just say take one or the other. Both functions would have been important. So that's the start. We had to correct this by finding the one explicit function. Here, y is now a function of x. And now we can use the chain rule, differentiate this thing, and get the slope of the tangent line at that point. Any questions with the steps to this stage here? Okay, before I get too far differentiating it, I want to mention one handy kind of formula that is just helpful because square roots come up quite a lot, especially in applications. They can be tied in with distances, for example. And so you'll often find that if you have y equals square root of x, you can differentiate this with taking quite a lot of steps, especially if you're simplifying it down. You could start by writing it as x power 1/2. Then when you go to write out y prime, ordinary power rule says that this would be 1/2 times x to the power of -1/2. And then you could simplify that down. You can move, if you wanted to, the base x to the denominator to make that power become positive. It would be 1/2 x to the power of positive 1/2. And then you could keep on going even further. This is now equal to 1/2 root x. So that's kind of a nice little demonstration of techniques from section 3.1. But where this becomes kind of useful is, here's a nice shorthand, or I guess we could say shortcut formula. This only works for square roots. There's a different formula if it was the cube root because you'd have power 1/3, different formula for the fourth root and so on. But my shortcut formula says d by dx of the square root of x. Instead of reproducing all of these steps, which is 1, 2, 3, 4, depending on how you count them, the punchline each and every time is you get to 1/2 root x. I've seen some people already using this formula in the homework, and so it's definitely kind of a convenient one. So I'll use this shortcut formula when I differentiate this, and I'll use it quite a lot as well as we go forward throughout the course. I'll remind us of the shortcut formula a few times that we're using it first. Now, back to this right here, if that's y, we want to compute dy dx, the derivative of the function with respect to x. But now as we observe, there are two functions here. Chain rule is necessary. There is the inner function, 5x power 4 minus x squared, and then there's the outer function, which is the square root function itself, kind of just highlighting the square root symbol to indicate that portion. So now at this stage, we're reviewing the chain rule. Let's pull it up for some guidance. Once we decide what function is inner, which function is outer, first thing we do is differentiate function number one, the outer function. So that's this f prime portion down below here for the chain rule. When we go to differentiate it, we're just using this shortcut formula, but we don't put in x, we just leave a whole big placeholder for x. So the derivative with respect of y with respect to x is 1 over 2 times the square root of something. Then we multiply by the derivative of something. So here I have the f prime part. I don't have a g of x inside there yet. That's going to be this entire placeholder with the square root. We multiply by the derivative of something, that's this part right here. And the thing in green, the inner function, just copies in both of those placeholders. So 5x power 4 minus x squared goes here and here. So that's what the chain rule looks like, wrong tab, for these particular functions that we're dealing with. Now that we got here, all we need to do is simplify this down a little bit further. Any questions to this step? Okay, let's take this a little further. By simplifying, we can now write dy dx equals, not much to do in the denominator, let's just copy it in, 2 root 5x power 4 minus x squared. And since we're multiplying something by a fraction, the whole result here will just multiply into the numerator. And so that's how we would typically write this out. Differentiate and place the result up into the numerator. Term by term, we get 20x cubed minus 2x. And finally, we can simplify this. It helps out just a little bit. 2 can divide from here and into both terms in the numerator to get us all together. 10x cubed minus x divided by the square root of 5x power 4 minus x squared. So this dy dx tells us the slope to the tangent line of this one function. Remember, there's 2 of them, but we're focusing on just this one explicit function. That'll give us the slope of the tangent line at any point x, or any input x. Our input is going to be at 1. So here's the resolution to the problem. When it says find the slope of the tangent line, the end answer is going to be, all right, m to remind us that's the slope. And this will be our last step. It'll be dy dx evaluated when x is 1. We peek at the graph one more time. We can see that the slope is positive. The curve, if it's increasing, the tangent line would look something like this if we drew it out, where the red dot is moving around. So we better get something positive when we go to evaluate. That's a good mental check on the work so far. Plugging 1 everywhere x is in this expression gives us 10 minus 1 divided by the square root, 5 minus 1. This gives us 9 over the root of 4, or a 9/2, slope of 4.5, which does definitely match this picture. This is increasing somewhat rapidly, not like y equals x, which would go like this, a 45-degree line. So 9/2 looks very plausible for that graph. So we did it. It was kind of a painstaking step-by-step procedure, because y squared equals 5x power 4 minus x squared is more than just that function, y equals the positive root 5x power 4 minus x squared. It's these 2 functions altogether that really is what that equation's encoding. So it's sometimes pretty painstaking and sometimes not even possible to solve for the variable y when we go to do this the standard way. So here's where implicit differentiation is going to start shining. We're going to redo the whole problem, start to finish, with implicit differentiation. Any questions at all, folks, with the first look in part A? Okay, now the implicit differentiation way. Let's get some clean space to focus on what's going to go on with this one. And wrong tab, I have too many tabs open. Let me pull this open again. So this time, we're going to just put in the curve y squared equals 5x power 4 minus x power 2. So that's our curve. It is not the graph of a function. It fails a vertical line test like we discussed, but it's a mathematical curve, and we can still address the question of what is the slope of the tangent line right at that point. So using implicit differentiation, here's what's going to look like. Let's start off with some chain rule review. The chain rule is still part of this, but sometimes it's really hard to spot how the chain rule is actually being used in the first place. In implicit differentiation, there is an implicit function, y equals f of x. But this time we don't want to solve for it. Sometimes we can. That was the f of x function here in part A when we did it before. But in other problems, that's going to be extremely difficult to solve for, or effectively impossible to get an exact solution on. So instead of trying to solve for y equals f of x, we know one is there. We just regard it as an implicit function. So this is our implicit function. And if y equals f of x, and we want to go to differentiate y squared is just going to be f of x squared in this notation. So now, viewing this through the lens of the chain rule, in a chain rule setup, f of x is the inner function. So that's our innermost function. The squaring function, the power 2 function, is going to be the outer function. So here's function 1. Outer is effectively just y equals x squared, but in place of x, we put in the entire function, f of x. Now let's imagine we're differentiating y squared. We need to do that with implicit differentiation since y squared showed up here. It would look like this, d by dx of y squared. Now we copy the process of the chain rule differentiation. We differentiate the power 2 function first. When we do that, the power 2 comes down. The new power in the group is just 1. Let me make sure that looks like a power 1, not a prime symbol. And then we multiply, we chain on a new derivative. So this is effectively the chain rule. So this time when we wrote 2, a placeholder power 1, that was the f prime part, the derivative of the outer function. And then we put in a placeholder, we used a bracket this time. We chained on a new derivative, and in both of these two empty spots, we're putting in f of x itself. So f of x going inside both of these would look like this. Here's the f of x here, and here. Let me make sure those parentheses don't get too compressed there. So there's the derivative, there's f of x copied into two spots. So now this is telling us dy dx, or rather d by dx of y squared equals 2. We have an f of x here, but from the very top of the notes, recall f of x is just y, so we can throw a y there, times f of x prime. Again, f of x is y, so we can just put in here y, call it y prime. And that's the derivative of y squared. If we use Leibniz notation, we could also say d by dx of y squared. The process is you first differentiate y to get 2y, but there's a function inside of there. Y is f of x, so when you differentiate y squared, there is an inner function. You have to multiply by the derivative of the inner function. That is the whole idea of the chain rule. So we chain on the new derivative, dy dx. The dy dx, you could either write in Leibniz notation this way, or leave it as a y prime. It will be up to you how you decide to write it. So in purple, this is the major idea for what's going on with implicit differentiation. Essentially, We don't try to solve for the variable y, no matter how complicated this looks. We just treat y as really a new function. So if it's y cubed cosine y sine y, it's really something like this. There's a function on the inside. Each time we differentiate, we follow the ordinary rules of derivatives, but we always chain on a new derivative. Y prime will always emerge. And that's this part right here, the chain rule, the g prime at x. So that's the logic of implicit differentiation. We'll go back up here, show the process in full, but any questions or comments at the moment? Okay, well, let's go back to this curve. Y squared equals 5x power 4 minus x squared. If it says using implicit differentiation, what we mean is differentiate both sides. With respect to the variable x, which seems weird. On the left-hand side, there is no variable x, but recall y is truly some function of x. We're just not going to solve for it this time like we did in part A. So if you differentiate this with respect to x, you get 2y times the derivative of the inner function, which is y itself, dy dx. And that dy dx is, once again, really just this part right here doing the chain rule. So that's the derivative of the left-hand side. When we differentiate the right-hand side, these all involve x, so it's a normal derivative. 4 is going to come down, multiply the 5, so 20 times x power 3 minus the derivative of a degree 2 function is going to give us 2 x to the power of 1, which will leave in as just a 2x. Then we can divide the whole equation by 2. Every term on both sides has a factor 2. So this is more simple to write in as y times dy dx equals 10x cubed minus x, which might give you some deja vu. That's the 10x cubed minus x part right here up in the numerator. Looks like we're kind of on the same track, which is amazing in a certain sense because we never even solved for y on this. Yet we can still differentiate for the right function we need to use. What we want is the derivative dy dx. So in the very next step, we solve for it by dividing by y. So now dy dx equals 10x cubed minus x divided by y. And we don't go a step further with that derivative. That's the implicit differentiation of the function y with respect to x. Notice we leave the variable y there because we never solve for what y equals. We just know that there is some function in the background, no matter how complicated that curve looks like. Last thing we want is the slope of the tangent line. So the slope is going to be m as a reminder. It means just take the derivative dy dx. That derivative dy dx is really pretty amazing because that's going to give you the slope of the tangent line at any point whatsoever that's on this curve if the derivative exists and the tangent line is not vertical, which would mean undefined slope. So even if we were right over here, some other point on the graph, so maybe somewhere there, anywhere that's a point on the graph that has a tangent line with a defined slope, that equation right there gives you all the information about the slope of the tangent line. This time we have to use the full coordinate. X is 1, y is 2, because we have both variables y and x. So we say evaluate the derivative. At x is 1, y equals 2, coming from the given point over here. When we do that evaluation, we're just plugging 1 and 2 in for x and y in the right corresponding order. So this becomes 10 times 1 cubed minus 1 over 2. So there's our coordinates being substituted in. But simplifying this down, this gives us just exactly a 9/2. Miraculously, the same thing that we had before. And I agree with Caleb, that's kind of impressive in a certain sense. When we did this at the first portion, sure, we got the 9/2 slope out, but we had to do all this extra algebra, and that algebra can explode. We had to make sure we selected the right curve as well at the same time. The derivative looked a little bit more complicated, but if you just use the chain rule in a really clever way, which we call implicit differentiation, this is the full process. And the big takeaway is every time you differentiate a y variable, you just tack on dy dx. Well, that's the full process. We got the same exact answer, which is comforting, and it's not a coincidence. If the slope exists using the part A method, it will also exist using the part B method, and in almost every single situation, that's the faster way to go. Well, any questions at all, folks, with the rundown, seeing this problem done two different ways? Okay, well, so far for the course, our major use for implicit differentiation is going to be a vehicle for us to differentiate inverse functions, logarithms, all the inverses to the 6 trigonometric functions in section 3.3. But implicit differentiation is an important technique in its own right. So we'll practice just more problems along these lines just to see how it goes. So here's our next example, part A. You could solve for the y variable on this one, but you would have to use the degree 3 function, not the quadratic function or quadratic formula to solve for this. The degree 3 cubic formula gets just worse and worse and worse. And there's some interesting facts algebraically that say if you have something like, say, degree 5, degree 6, there is no formula for these things. So once again, this is where implicit differentiation really shines. We'll focus on part A, come back to part B later. And that punchline we mentioned before is essentially differentiate both sides with respect to x. But every time you differentiate the y variable, we tack on a dy dx. So going left to right, here's what the derivative is going to look like. Derivative of 2y cubed. First power 3 comes down, multiplies the 2 to give us a 6 times y squared. But there are really two functions here. There's the cubic function, and then there's the y equals f of x function, the inner function. So we multiply by dy dx. So let's use a different color. Let's go with green. Because that's the function from the chain rule that always got chained on. We always use the color green, so that's the best color for this one. And again, you could call it y prime if you prefer. I think the notes in the book usually use dy dx, so that's why I'm emphasizing it here. So now we just go term by term. We use all of our prior rules for differentiation, and then the chain rule just tacks on dy dx when we're differentiating the y variable. So if it's a y squared, we go plus 2y, y power 1, but y for short, times, tack on dy dx through the chain rule, and then just do it again one more time, minus 5, y to the power 4 times dy dx. So that's the entire left-hand side. When we go to differentiate the right-hand side, this is just taking the derivative as normal. So using the power rule multiple times, we get 4x cubed minus 6x squared plus 2x. We want to compute dy dx, but computing dy dx, for us, what this boils down to is we must solve for dy dx. So now there's just a bit of algebra to get dy dx isolated in one side, and then our work is going to be complete. In other words, that's the end of the calculus step. Any questions at all, folks, with the implicit differentiation? Okay, this becomes a pretty decent algebra review. If you're solving for a variable that's kind of just smeared across multiple terms, our ultimate method here is to factor. So we can rewrite this as 6y squared plus 2y minus 5y to the power 4, dy dx factors out, still set equal to 4x cubed minus 6x squared plus 2x. And then last thing we can do to isolate for the derivative dy dx is just divide out that entire group as you see it. So we're on our last step, dy dx is now equal to 4x cubed minus 6x squared plus 2x. Divide by, now place this entire thing in the denominator, 6y squared plus 2y minus 5y to the power 4. So that's our derivative, and at this stage, all the work is complete. There was no further question about what would the slope be at a certain point or what will a tangent line equation will be. But another thing that's kind of fun with these is once you have that derivative down, it's interesting to take a look into what was the curve in the very first place. So let's sketch it to see what it was. If I can find a spot to put this, give me a moment. Okay, that sort of fits. Should have thought ahead on where I was putting everything when I was drawing this out. Okay, so there's dy dx. Here's the curve we're going to place over here. And Desmos is a pretty nice environment for just visualizing this kind of work. If you need a graph readout in an exam setting, I'll print that actual graph on your exam itself. So there'll be no need for you to worry about not having a graphing calculator. When you do these as homework problems at home, it's not a bad idea to graph these as we're about to do so. Once again, just to get an extra feel for what you just produced. So that whole thing can go in just as you see it, 2y cubed. I want to put it equals and put in x power 4, just so we can see what happens to this curve as we put in more and more. As it stands, that passes the vertical line test, so you can solve for y and get one unique function of a variable x on this. But there's more to the story, so if we add y squared, it changes. It puts a little loop down here. So now this is no longer the graph of a function. Fails the vertical line test immediately, thanks to that weird structure that emerged just from adding in a y squared. It can get weirder still, subtract y power 5. And now it looks like some kind of, almost like a coat hanger kind of thing going on here. Looks like a weird exclamation sign, another curve down below. Almost feels random on how these get put together, but it's not random at all. This is just the structure this curve is encoding. Then it's minus 2x cubed, and now it's warped a little bit. It's all connected, but still absolutely fails the vertical line test. Add x squared, and this is our function. Now it's in two discrete pieces. One curve here, one curve here. They're disconnected. This one has an odd looking loop-de-loop. It's symmetric. That's essentially our underlying function. Let's put it down for just a visual. Ordinarily, we can't do calculus on that because our calculus requires a honest function, passes the vertical line test. But what's amazing about this is when we see that power 5, there's probably 5 different functions all together making up pieces, chunks of this overall curve. And it doesn't matter. You don't have to solve for what functions there are. This is going to give you the slope of the tangent line. At every single spot, the slope exists. In other words, we can find the derivative, the slope of the tangent line, at any spot the derivative exists, whether we're on one weird piece or another weird piece. That's the complicated formula that gives you that slope guaranteed. Really, probably the hardest thing is to get an exact point, an exact coordinate on this graph, so that you know you're putting in the exact values and getting the real slope. So that's the power of implicit differentiation. It's a strange technique, and it gets stranger and stranger the more we use it. But the fundamental idea so far in the notes in section 3.5 is this idea. Even if y is solved for, you can still differentiate. You use the differentiation formulas as normal, but multiply by dy dx, you're essentially just using the chain rule. So that's another example down. We'll try out another one, which uses more differentiation rules. Product rule will be the major one for this next one. But any questions for this problem here? Okay, let's turn to next. This curve, and hide example 3 down below. This is one that gets really very weird. So when you go to plot something like this one, here's where it's going to show, once again, how implicit differentiation really shines as a very, very powerful tool. Let's start by plotting just y equals x. That's an ordinary nice curve. Let's add bits to it. Put in sine x squared. If you have a sine x squared, here's how it now changes. We made it really pretty complicated with that x squared. It kind of looks like this is still the graph of one single function. I think that would be true. Looks like it would have a lot of domain issues. If you were to isolate y by dividing by x squared, you would lose an element in the domain wherever sine x squared becomes 0. But there's more to the story because there's sine of y squared on the right-hand side. There's really no way I can think of how to solve this function for y, because to free up y squared, I'd want to use, say, the sine inverse function, but that's complicated by x multiplying. And I'd also have to use sine inverse on the left-hand side, which would trap the variable y as well. So solving for y in this configuration is just not part of my toolkit whatsoever, but that's okay. We can still do calculus on this. So throw in sine y, and now it's this weird looking diagram. Looks like some kind of evil looking structure, but that's still not our function. It's y squared. And here's our curve. We zoom in, it looks kind of tame, but there's more to the story of this curve. This is a very, very complicated curve. It contains y equals x, our original part, but then it has all these weird wavy oscillations, some horizontal, some vertical. It looks like it has quite a lot of symmetry, but the more and more you zoom out, the more you realize there is not a finite number of functions that relationship in part B is describing. This fails the vertical line test spectacularly if you try to isolate each component function, like we did in, say, example 1, part A, to find the explicit functions. There's infinitely many of them. The more you move off out here, the denser the oscillations go, and this is the stage at where Desmos is just failing. It can't plot to the resolution it needs to, so these are just graphical anomalies way off here. So out of nowhere, we have something with just an extreme amount of structure. These kind of relationships and functions just get weirder and weirder, but we can still do calculus on that. That's the amazing part. Well, let's throw this down just again to see the visual of what we're dealing with when we put down a relation like that in part B. Here's the wild and chaotic landscape we're differentiating on. If you find the derivative to the curve in part B, then at any point you can find here where the tangent line has a defined slope, put the coordinates in for that point into our answer, and it will describe the slope to the tangent line. So that's amazing when you consider just how much structure there is in this curve down below. So let's move the curve off here just so it's not too distracting. And now do the heavy work of differentiating all of this together. Now, before we take the derivative, notice the derivative is going to be tougher. And it's not the implicit differentiation part that makes it tougher. It's the fact that we have to use product rule. twice. So let's set up our color coding for product rule like we've done in the past. On the left-hand side, the first factor is y, and the second factor is sine x squared. On the right-hand side, the first factor is x, and the second factor is sine y squared. So when we go to use the product rule, first, let's focus on the left-hand side. We'll differentiate y. You could call that y prime, or I'll go once again with dy dx. If it's just y alone, it doesn't become 1. You could say 1 times dy dx. A dy dx is always going to emerge when you differentiate a y variable. If it's just y to the power 1, this is all that happens. You get dy dx itself. Then we copy sine x squared. Go plus for product rule, copy the factor of y. We're not differentiating it, so no dy dx there. And next, differentiate sine x squared. But when we go to differentiate sine x squared, that's a chain rule that comes out of nowhere. So this is product rule twice. And chain rule. So let's set up the derivative for the chain rule on this one. First, we differentiate the outer function, which is the sine function. And let's actually copy the method we've said before. Here's function 1, outer. We won't do this every single time, but we just learned the chain rule. So let's put down our analysis for it, like we did last class. Here's function 2, inner. The inner function is x squared. The outer function is sine x. So when we go to differentiate the sine function, we get cosine. We put a placeholder there. Then multiply by the derivative of a new function. If we're multiplying by the derivative, don't forget the prime symbol. It definitely is important. Now take the inner function, throw it in both of those spots, both here and here. And that's the run through for both product rule and chain rule for left-hand side. Then we just redo it all over again. Same analysis on the right-hand side. We're going to use the product rule. Take derivative of x. That's just going to be a 1. I'll put it down just so that I know we covered that. Here's the derivative of x. Copy sine y squared. Go plus, copy x. But then multiply by the derivative of sine y squared. Now, this one's a chain rule as well. So here's the analysis on this. Here's function 1, outer. Function 2, inner. So upon differentiating sine, we get cosine once again. Throw in a parenthesis. Multiply by a new derivative getting chained on. And just plug the inner function, but this time it's y squared in both of those placeholders. So y squared will go both here and here. And now when we go to do the derivative of that y squared, that's a whole new chain rule, but that's just still differentiating implicitly. That's where we're going to get another 2y times dy dx. So that's the story so far. We have 2 derivatives to finalize, derivative of x squared, derivative of y squared. Any questions at all, folks, with getting through all those rules? Okay, well, let's finalize this. Usually when we write out derivatives like dy dx, sometimes it's a good idea to put in the function like sine x squared first, and then put in dy dx. Oftentimes we want dy dx on the far right-hand side when we go to format this. Not strictly required, but it seems to flow a little bit better that way. Then finally we get plus y, cosine of x squared, times derivative of x squared is just a 2x. Now, way over here, we have sine y squared plus x cosine y squared. And now, last derivative to take. We're still differentiating implicitly, so this becomes times 2y. Because y is really a function of x, we still tack on dy dx. So we have a dy dx in two spots, on the far left, on the far right. If we subtract the term that involves this dy dx to the left-hand side, we can do what we did in part A, factor out dy dx, divide by the factor in front, and then be done with the problem. So at this stage, we're done with the calculus. And just to format it slightly more clean, let me take this additional step. We're now looking at sine x squared, dy dx. Let's reformat this term as plus 2xy cosine x squared equals sine y squared plus, let's reformat this entire term as plus 2xy cosine y squared dy dx. So I didn't really do much algebraically, but just put things together in a way that these kind of things would be typically written out, just to make it easier on the eyes on what's moving around where. Now, anything that has a dy dx, we want just on one side of the equation. So I'm going to start by subtracting out 2xy cosine x squared from both sides, removing it from the left-hand side, and also subtract 2xy cosine y squared times dy dx from the right-hand side, removing it from the right-hand side. So when we do those swaps, we get sine x squared dy dx. We're subtracting this entire term, so minus 2xy cosine y squared dy dx. Caleb says, why do we move the sine x squared to the other side of dy dx? No big reason that's completely required. For me, it's more just a formatting issue. Usually when you write down, say, a dy dx, it's sometimes a good idea to put everything to the left and just the derivative to the far right. Because sometimes in this format, there could be a miscommunication, or hang on, where did I move that? Oh, over here. Let me start over my comment. I was looking on the wrong line. We had dy dx on the right. On the left, we moved it over to the right-hand side, only just to be explicit about when we took d by dx, we weren't differentiating with respect to x on the function y sine x squared. The derivative just ended on y. It's pretty much what we meant here. So if you left it in that format, it's okay. But once you write it in like this, putting dy dx to the far right, there's now no chance of a miscommunication that the derivative just ends on y. It's not differentiating sine x squared. Other questions at the moment? Okay, so we've got this part copied down. We subtracted the 2xy cosine y squared times dy dx. So here it is on the left-hand side. Also, we're subtracting the 2xy cosine x squared. So I'll write it as sine y squared minus 2xy cosine x squared. So that's our algebra. There's so much stuff that it's hard on our eyes to see how it flowed. Essentially, this moved over here to the right-hand side. That's why there's a negative sign in front of it. And this part moved over here to the left-hand side. I think the arrows help out a little bit. If they don't, definitely don't copy them down. So it moved over to the left, so there's a negative sign there. Last thing to do is just factor out the dy dx. Essentially, we're at this step right here. We want dy dx in just one spot, so we can do a division. So factor out dy dx, and we'll get sine x squared minus 2xy cosine y squared times dy dx equals sine y squared minus 2xy cosine x squared. And we're just about there. We have found the derivative to the original curve described in the relationship in part B. The moment we come way down here and isolate dy dx. So the slope to the tangent line at any point on that mess down there looks monstrous in a certain sense, is given by this formula. Sine y squared minus 2xy cosine x squared, then divide by this entire group. So it's being divided by sine x squared minus 2xy cosine y squared. There's some pretty strange symmetry that we're seeing here. We have sine y squared divide and then sine x squared from top and bottom, cosine x squared and cosine y squared going from top and bottom as well. So interesting symmetry in the derivative itself. There's symmetry in how the curve is defined, going from y to x's from one side to the other. And the graph looks very, very symmetric at the same time. So that's another look at implicit differentiation. This one got ugly just because there were a lot more terms when we used the product rule twice and then the chain rule once, getting through the process. But that's the whole flow. You'll see some problems kind of like these. Some of them a little bit more routine, like in part A. I think one is a little bit more algebraically challenging. This will be a good one to take another look at, like this one in part B in the homework. But this is our tour for implicit differentiation. We have one more to take a look into before we go to the next section. But any questions or comments to this stage? Okay, so aside from crazy, crazy curves like that one, here's a little bit more tame of a curve. Here's our example 3, the last example for the notes. This curve, some of them have famous names, which is interesting. And this one happens to be called the Devil's Curve, which is, I don't know why it's called that, but that's interesting in a certain sense. What we want to do is use implicit differentiation to find the equation of the tangent line at the point 0, -2. So this is a kind of problem where if I want you to get the equation of a tangent line, I just want to give just a little extra help in an exam setting, you might have a graph like this one that's been printed out. The reason it helps a little bit is sometimes you can get a hint on these. Like, what is the slope of the tangent line if you know the point on the graph? Our point is at coordinate 0, -2, which looks like it would be right here. And it also looks like, if it's right there, our tangent line should be horizontal. That's not a guarantee, but our slope should be pretty close to 0, at least, by the image that we're seeing right here. And that can help us out when we go to do this algebraically and then using implicit differentiation. So this time we want the full-on equation of the tangent line at that point. We're going to use implicit differentiation. And first way to start this off is undo all that factoring that's been done. So let's distribute y squared inside to make differentiation easier. This will give us y power 4 minus 4y squared. Now we don't need the product rule on the left-hand side. We already got through that on the prior example. The same idea over here. You don't need the product rule on that. Just distribute x squared in and you save a lot of time and effort. This is x power 4 minus 5x squared. Then back over here, now we differentiate implicitly, but not as bad as what we've seen before. The derivative of y power 4 becomes 4y cubed times dy dx. Then we just keep on repeating that process. Variable y comes in, again on this next term, so this becomes -8. Y to power 1, so just y, times dy dx through the chain rule once again. Now we have x's on the right-hand side, so ordinary derivatives give us 4x cubed minus 10x. And we're kind of over the big steps algebraically. We just need to factor out dy dx. If we do that, we have 4y cubed minus 8y times dy dx equals 4x cubed minus 10x. And it can be helpful sometimes to reduce the equation, either at this step or on the next step. Everything can be divided by 2, every single term. I should have noticed that in the prior line. If we divide everything by 2 again at this line, we would get 2y cubed minus 4y times dy dx equals 2x cubed minus 5x. Not completely required, but once again, if you can cut the size of the numbers down, sometimes that's a good idea. Now, we almost have the first step on getting a tangent line equation. We need dy dx, the slope at any point. So dy dx is now equal to, take the 2x cubed minus 5x, divided by that entire factor, 2y cubed, minus 4y. So that's the first step whenever we're trying to get this equation of a tangent line. Any questions at all, folks? Getting the dy dx on this term? Okay, the next step we always take is we now just come up with the slope m. M is going to be dy dx, but now evaluated. And back in the day when we did this, we evaluated at just one value for x and we were done. But now we have a formula involving both x's and y's. Let me fix that. I'm not sure what I did there. Now that we have a formula involving both x's and y's, we use the full point. This is evaluation at x equals 0, y equals -2. So plugging that in, we're throwing in 0 for x's. So this is 2 times 0 cubed minus 5 times 0. And then down below, we're throwing in -2 for y's. So this is 2 times -2 cubed minus 4 times -2. But with what we have going on in the numerator, the whole thing is 0 since the numerator is 0. And that's what we were probably predicting here. If you have a horizontal tangent line, that does mean the slope is 0 on this. So is the graph needed for us to do the problem? Not at all, but if this was a problem on a real exam, sometimes I'd like to include the graph so you can see how reasonable is your slope. For example, if I got a slope of 5 or -3, it wouldn't make sense on this graph at all. If the point was here instead, where the red dot is, I'm expecting a positive slope and so on. So it just gives us a kind of a further check in our work once we get to that step there, finding the slope. Last step, the equation of the tangent line. Well, if it's a horizontal line, the equation is always y equals some number. And the number has to be that -2 right there. So our work is done. This is the equation of the tangent line. The moment we just throw in the second coordinate. But again, you might have predicted that from right here. That horizontal line is exactly the line, y equals -2. Well, that was our last problem for implicit differentiation on this section. We're going to use it some more in the next section to come up with a new slew of derivatives, derivatives of the logarithmic functions. But any questions at all, folks, getting through these problems here? Okay, well, we're getting pretty far through the differentiation formulas in chapter 3. The next big batch of formulas is now, let me clear that off, that just looks kind of oppressive when I see it, is now derivatives of logarithmic functions, our next classification of functions. So here's our section 3.6. I have a revision here because I noticed a typo. If you printed these out already, sorry about that. I noticed it just this afternoon. On example 2, part C, I think that was a number 5. It was meant to be a variable t, so 7t minus 4. So that's the correction to make. Again, sorry for missing that right there. Okay, here's how this section starts off. It just completely spills the beans for us. It tells us right away, if you're taking derivatives of logarithmic functions, here are the rules. The derivative of a logarithm to base a of x is interesting. It's just 1 over x times the natural log of a. That might remind you of how, say, the derivative with respect to x of square root x is 1 over 2 square root x. So likewise, for the logarithm, you just go 1 over x. If it's to base a, you multiply by the natural logarithm of a. But if the base is e, we know that the natural log of e is 1, and so it simplifies to this nice formula. The derivative of the natural log of x is just 1 over x, a really friendly formula in a certain sense, which is going to cause all sorts of interesting havoc later on when we look into antiderivatives and integration. It turns out, even though this is not something that comes up a lot in these notes, that's a formula we're going to come back to with integration. The derivative of the natural logarithm of the absolute value of x is 1 over x as well. So whether it was x or absolute value of x, it resolves to the same exact thing, just 1 over x. And this one's just a generic formula if you have an arbitrary base, like say log base 7 of x. So those are our formulas. There's a whole bunch of white space down below because I feel like this was a good idea to, like we hinted at, connect the dots to implicit differentiation to show just where in the world this formula actually came from. Not all the formulas that we've seen here are easy to prove. The derivative of sine being cosine is difficult. It's in the reading over several pages. But this one's not too bad. It's just reviewing implicit differentiation. So for that reason, we'll do a derivation here. What I want to derive is this line here, the general formula for any valid base, that we get 1 over x natural log a when we differentiate log base a of x. To do that, we're going to need some review. One review is if you take d by dx of a to the power of x, you get a to the power of x times the natural log of a. So we saw that in section 3.1. We'll need the derivative of the exponential function in order to come up with a derivative of its inverse, the logarithmic function. So our first step in this derivation is we just write down the function we're dealing with, y equals log base a of x. So there it is in its full glory. We want to differentiate that, but I can't just use that formula. That's what we're trying to derive. That'd be some extremely circular logic, right? So to come up with this derivative, we have to do something else. We could write down the limit of the difference quotient, like we would have done in section 2.8, but then that limit becomes fantastically hard. I would just get stuck at that step. But we know that derivative, that's a humongous upper hand to us. We're going to use that idea, that the derivative of the exponential is just given there, and put an exponential into the problem. So if that equation is true, the exponential equation, a to the power of y equals a to the power of log base a of x. That one is also true. This is the equation in logarithmic form, and this is the equation now in exponential form. And the reason this is a decent idea for us is, let's go to the logarithms review material on the top of the Canvas notes. We can now use property number 2 of logarithms. B to the power of log base b of x is just x for all positive values of x. X is defined to be positive here because that's the domain of log base a of x in the first place, positive values of x. So we can just cancel off that entire thing, and our next line is that a to the power of y is x. So we started with something we don't know how to differentiate. we have this down. It's a brand new equation, but let's go up to the top here just for more vertical space. If we take a look at a to the power of y equals x, we do know how to differentiate that equation there. The derivative is looking at us at the right. There is a little bit more to the story though, because this requires implicit differentiation. So implicit differentiation gets used at this step here. We're going to differentiate both sides with respect to the variable x. If we do that, here's what we're going to get. Let me write out kind of like this. We have an inner function, a, an outer function, y equals f of x. We just don't know that function, or we're pretending not to know that function. We know it's right there. Y is log base a of x. So we're going to consider this to be the inner function 2, and the outer function, derivative 1, is y equals a to the power of x. We differentiate something like that just in the last section notes, prior sections notes 3.4 in the chain rule. The derivative of this is going to look like this format. Differentiate the outer function. You get a to the power of something multiplied by the natural log of a. And that's just this formula right here that we're using. Then we have to multiply by the derivative of the inner function. We'll call that times dy dx. So that's the essence of the chain rule. That's the idea of implicit differentiation. And that's what the derivative will look like on the left-hand side, except I put dy dx here. I also have to copy in y in that spot there where the placeholder went. On the right-hand side, we differentiate x. That comes out as just a 1, so that's the nice derivative. And we're basically there. We want to solve for dy dx like we did in the prior section notes. So if we solve for dy dx, we get that this is equal to 1 over a to the power y. So that's our next step so far. And to some degree, it feels like we're kind of just stuck right here. But we're not really, because we started with knowledge of what y actually was in the first place. We said y is log base a of x, the thing we want to differentiate. But we didn't know that derivative, so we transferred it into an exponential function, so we can use the exponential derivative. But what that all means is we can plug y back in on this very bottom down below here. So now dy dx equals 1 over a to the power of, put in a substitution for y, log base a of x, and then cite properties of logarithms yet again. Properties of logarithms say, well, we used property 2 already, but it's property 2 again. Excuse me, got confused on those. Property 2, just like before, says b to the power of log base b of x is just x. So we can, oh, hang on, I forgot one additional piece. There's a mistake right at that step. Almost got it all in. Yeah, thanks for spotting that, Logan. I just noticed that, and then I noticed the chat. There was the natural log a here. When I went to divide by a power y, it should have copied into this spot right here, natural log a. Thanks again for noticing that, Logan. So natural log a also goes here. And now finally, it's the right time for the cancellation. We cancel that ways, and we have dy dx is now equal to 1 over x natural log a. So let's zoom out to see how close we were to our target. We're trying to get to 1 over x natural log a. We were never going to get there without that natural log a appearing right over here once again. So again, thanks for catching that. And now that's the completion of the derivation. And essentially, any function and its inverse you know the derivative of the function, you can come up with the derivative for the inverse using the tool of implicit differentiation. So this is one of the massive applications of why we studied that skill. And for the moment, it gives us just two new derivatives that we can take a look into. So this derivation was really just to review implicit differentiation a little bit more, think about properties of logarithms, review that derivative there for the exponential. But any questions at all, folks, getting through the derivation? Okay, what we want to do next is just practice taking more derivatives using these new formulas that we have here. I also want to mention there's quite a bit going on in this section. It's called derivatives of logarithmic functions. But as you scroll through, you'll notice trigonometry makes a comeback. Every one of these functions, all 6 of them, has an inverse if we restrict them to the right domain. And using the same strategy that we did with log base a of x, you can come up with the derivative of their inverse functions. So we'll take a look at these after we review working with logarithms. But this, again, is all just what we get with implicit differentiation. The textbook shows how to do sine inverse and I believe tangent inverse as well. And this is the full set of the derivative of every inverse function of the original trigonometric functions above. So before we get to those, let's practice a little bit with the new tools that we have so far and differentiate some functions. One big idea, however, is because we're dealing with logarithms, you want to have this pretty much always ready to go. Much like if you're in section 3.3, if you're doing the derivatives of trigonometric functions, pull up the notes for trigonometry, look over how they're defined, look over how to do evaluations, look over the identities. And these are just essentially the identities for the logarithms. The reasons these are so helpful is if you look at some of these functions really closely, you'll start to notice you don't have to work as hard as you might have thought. Natural log of x squared, well, you could rewrite that as f of x, natural log x squared. I didn't do anything big there, I just forced in function notation, but then use property number 7. Property number 7 says any power on x, like say that power 2, becomes a coefficient. So this is just 2 times the natural log of x. Now we can use the formula d by dx of natural log x is 1 over x, which means our work is essentially just done on this one. It's not the chain rule at all. We'll see some where the chain rule is unavoidable, but my strong suggestion is always look before you leap. Try to find a way to make properties of logarithms work for you, and the derivatives can be just as fast as this sometimes. F prime at x is, constant multiple rule says 2 stays where it is. Multiply by the derivative of natural log x, that's just a 1 over x. And so the whole result is 2 over x, and the whole work is done right at that stage. Kind of satisfying as a derivative in a certain sense. So this is kind of like just real life, really. You don't want to work as hard as possible if you're doing a job, whether it's differentiating or something maybe for a real job beyond this class. You want to find a way to work as little as possible. And this is what we're doing here. Try not to use the biggest tool like chain rule, but it's really just the constant multiple rule by rearranging the function. What's one down? G of x goes differently though. That's a product rule. There's nothing we can do with properties of logarithms to avoid the fact that that's a product rule. So sometimes it's a chain rule and there's no getting out of it. And we'll review the product rule on this one to see how it goes. But any questions or comments at all with part A? Okay, well, even though this is a product rule, this still actually goes pretty fast. Well, if we go to differentiate this one, g prime at x, first we differentiate the first factor, natural log x goes to a 1 over x and its derivative, then we just copy sine x, go plus, copy natural log x, then take the derivative of sine x, that becomes cosine x, and our work is done right at that step. You could reformat this if you want as, say, sine x over x plus natural log x cosine x. But that wasn't really doing too much, really, algebraically. That just looks a little bit cleaner to my eyes. And this is just fine as well if you stopped at that step. But that's the whole story to that one. Really, we're just using that tool right there and combining some of our prior formulas, rules for differentiation. So that's 2 down. We're on a roll with these. I have a few interesting ones to take a look at the next example. Any questions at the moment before we go to example 2? Okay, so here's our next set. And you know what? Let's take this down as we go, just so we have a quick reference on properties of logarithms on each of these. Just like trigonometry, once you get into logarithms, this is a good time to start actually reviewing them in earnest from Pre-Calculus 1 class. And here's the hint: use properties of logarithms where possible. But we have to know when that's possible. On part A, here's a running theme in algebra. Pluses and minuses tend to mess stuff up. For example, if you have square root of x squared plus 5, we're kind of stuck here. I can't take the square root of x squared plus the square root of 5. We're just stuck right at that step. And same idea with this logarithm. If there's pluses and minuses separating terms out, nothing here supports simplifying that down. There's a product rule, a quotient rule, and a power rule, but not a sum and difference rule. So we have to go at this from scratch using the chain rule and really nothing else to attack it. Maddie asks, will the properties of log formulas be on our test, or will we have to write them down in our notes? For these should be included on the notes if you feel a little bit rusty. So let me put here just for a reminder, this must be on notes, not included on exams. Other questions at the moment before we launch into that part A? Okay, well, if we can't use properties of logarithms, like it's the case in part A, one tool we still have is the chain rule. Notice the chain rule is like a rule of last result. We only use it if we have to. And here's a case where we absolutely do have to. There's a composition of functions that cannot be untangled this time. The inner function, the derivative will take seconds, so derivative 2, is the degree 7 polynomial. The outer function, the first derivative will take, derivative number 1, is the natural log x function. So here's what it looks like when we go to differentiate it. Y prime is first, the derivative of natural log x. And it's a new derivative, so let's copy it here on the margin. Just for the refresher, the derivative of the natural log x is nice. It's just 1 over x. So when we go to differentiate that, we just get 1 over, put in a big placeholder there. Because it's a chain rule, chain on the new derivative. Then as we've done before, on essentially, I believe, every single chain rule problem, now take the inner function, plug it into the remaining placeholders. 5x power 7 minus 13x squared minus 9x plus e, and then again over here, 5x power 7 minus 13x squared minus 9x plus e. So that's step 1 on the chain rule. And actually, this goes a lot faster than you might realize. Oftentimes, people skip the step that's in the middle right here. We did it in the middle because we're learning the chain rule, and this is a new function with it. But notice what happens really. Whatever's inside the natural logarithm, it goes right down to the denominator, copied exactly as is. 5x power 7 minus 13x squared minus 9x plus e. Then we take the derivative of the inner function, but because it's multiplying a fraction, it just multiplies times 1 in the numerator. So we're just going to shove that whole derivative up into the numerator that we see right here. So differentiate this, we get 35 x to the power 6 minus 26 x minus 9. E is a constant, so it goes to 0. There's no x there on that last term. And that's the whole punchline. Whatever's inside the logarithm, it just gets thrown under the bus. It's down in the denominator. And you differentiate whatever it was, and that goes up into the numerator. So whenever you see a function like the one in part A, that's really all we have to do with it. Well, that's part A down. Any questions or comments on getting through that one? Okay. Part B is kind of similar. Part A was a natural log of a bunch of stuff. Part B is the natural logarithm of a bunch of stuff, but the big difference is there's one term there. Everything is being multiplied. We have essentially three different factors, 3x and e to the power root 7x. That means we can use property number 5, the product rule. That's stated with two products, x times y, but it could have been x times y times z. We would just add on plus log base b of z. So if you have things are just being multiplied together, you can rewrite this as natural log 3, there's the first factor, plus the natural log x, second factor, plus the natural log of e to the power root 7x, that whole entire third factor. So that's just property number 5 working really hard for us. And we should, again, never be fully satisfied. If you've used one property of logarithms, take a close look and see if you can use other properties. Nothing to be done on natural log 3, natural log x, but for natural log e to the power of root 7x, that's property number 1. It looks different because that's log base b of b to the power of x, but natural log is log base e of e to the power root 7x. That's an automatic cancellation. That cancellation is actually really huge. So observing that step right there makes the rest of the problem way, way easier to get through. The original function f of x is nothing but natural log 3 plus natural log x plus the square root of 7x. And this is much, much easier to differentiate for us. So let's take the derivative on the next step. F prime at x. And let me see where to scroll to on this. We have that the derivative of the natural log of x. Let me fix that. Almost looks like there's a negative sign there. Is 1 over x. But watch out for that. That's not natural log x at all. That's just a constant. It's a number just like e. It's a different irrational number, but because it's a constant, that first one goes to 0. Let's write that in to just emphasize. The derivative of natural log 3 is not 1 over 3 whatsoever. It has to be in this format. There must be a variable x. If there isn't, that's constant and it just goes to 0. Making that first term kind of tricky. We have to train our eyes, like we mentioned before, on recognizing what parts are constants and what parts are not constants. Not constant means for differentiating with the variable x, with respect to x, x occurs. So that one's an ordinary natural log x. Its derivative is 1 over x. And finally, we have that derivative to take. Here's the shorthand that we mentioned on, I think, the start of the section notes, 3.5. The derivative of respect to x of square root of x is 1 over 2 root x. That's, again, a pretty decent shorthand. So if we go to differentiate this, yet another chain rule, the reason the square root of 7x is chain rule once again is because it's not just x. Anything extra going on inside of there makes it a bona fide chain rule. So over here, the inner function is 7x. The outer function is y equals root x. So when we go to differentiate that last one right here, we get plus 1 over 2 times the square root of something. Here's that formula here where we put in a placeholder for x, multiplied by the derivative of whatever that something was, which is the 7x. So that plugs in both here and here. Notice the parallelism, it's pretty similar to how we set up part A, where we did 1 over x, so something went down below. We multiply by the derivative of whatever that something was. Only difference was it was a square root, so we had 2 times the root of something. But really strong parallelism when you look at this part, together with that part and that part there. So let me copy these just so that we have them ready to go. Last step finally is that f prime at x is 1 over x plus, let's take all this stuff here, 2 root 7x down below. The derivative of 7x is just 7. And this is a good stopping point here. You don't have to rationalize your denominators. So this would be a good spot to end at. So using properties of logarithms made this one a lot nicer. If you didn't use properties of logarithms, it's both a chain rule together with the product rule together with another chain rule because it's e to a power root 7x. And that chain rule actually involves 3 functions. The base, the exponential is the outermost. The square root is the middle, and 7x is the inner function. So if you did that from scratch, it's actually a lot of work to do that. By using properties of logarithms, even though it took a couple lines to write it all out, it saved us, I would say, probably a whole page of work, really, if we were to write out every single step doing that from scratch. Really, the takeaway point is, the selling point is, you really cannot ignore properties of logarithms. Not for any of these problems here in the homework or an exam setting. Always keep them at the ready. Calculus always intersects with algebra. We can't separate one from the other. But any questions at all, folks, getting through that part B? Okay, well, looks like probably one more problem for the day. And then I think will be a pretty good stopping point for us. We're going to save the derivatives of inverse trigonometric functions and examples down below for when we come back tomorrow on Thursday. So we're a little bit more fresh to look at this wall of text for new derivatives. So let's get through part C here. That's kind of a big problem on its own. I think there's a problem similar to something like this one on the homework as well. So if you see something like this on the homework and it feels like you're writing down tons and tons of steps, it's never intended to be that bad. If you're writing down tons and tons of steps, that's probably bad in a way because that's hard to do in an exam setting. So anything like this, think of this as being a dead giveaway. That we need properties of logarithms. I'll just say logs for short. I think that's the international shorthand for that. There's a lot going in here. So first, we're just simplifying the function. And when you say simplify, that term is overloaded. It depends on the context. This is simplified for some contexts, but if your goal is to differentiate, it's the worst possible format. So if you remember back in the day in a pre-calculus class, pre-calculus 1, there are problems that said, rewrite this, use expanding as much as possible so that you have multiple terms, none of the things on the side raised to a power. That was all just a preview to the calculus problem we're about to do here. First thing we're going to use is the quotient rule. And if you have a lot of practice on this, you can do it in one step, but we're going to really review properties of logarithms and take multiple steps on it. Use the quotient rule because we have a division here and just split this in two. This can be rewritten log base 7 of t times 7t minus 4. It's written as a square root, but we'll write it in as a power of 1/2, since that'll be useful for us when we use property number 7. Then it goes minus log base 7 of t power 5 plus 3 cubed. So that's property number 6. We can split a quotient. Now over here, we want to use property number 5. We can split a product. So we can say that this is also equal to log base 7 of t. In the product rule, we have a plus. In the quotient rule, we have a minus. And that's true whether you're talking about calculus or properties of logarithms. So go plus log base 7 of 7t minus 4 to power 1/2. And then I'll just copy this one in as well, just as it is so far. Minus log base 7 of t power 5 plus 3 to the power 3. So we started with the quotient rule. We split this one up with a product rule. And we're still not done. Two of these derivatives, the last two, are still challenging. But if you use the power rule, property number 7, every exponent p that you observe here can become a coefficient. So 1/2 can just move out in front. Same with the power 3 right here. And this is now log base 7 of t plus. Move the 1/2 through the power rule into the coefficient position. 1/2 log base 7 of 7t minus 4. And same with that power 3. It becomes minus 3. Log base 7 of t power 5 plus 3. Now, because there's pluses and minuses on the last two logarithms, there's no further steps we can take on this to simplify it down. We're essentially done with the properties of logarithms, which means we can calculate the derivative z prime. So that's our rundown, expanding things as much as possible. Any questions with the algebra review side? Okay, well, we have 3 derivatives to get through, but none of them are too bad, really. Let's review the property we need. The differentiation rule says the derivative with respect to x of log base a of x is almost like the natural logarithm property, but we multiply x by natural log a in the denominator. That means term 1, it's really just a formula evaluation. The variable is t, so we go 1 over t times the natural log of 7, and then our work is done. Scooting over to here, we have a constant multiple rule. We'll take the constant 1/2 times this derivative here. These are now chain rules. The outer function on both of them is log base 7. The inner function on both of them are those things highlighted in green. So using the chain rule, first we differentiate log base 7. The format is to go 1 over something times the natural log of 7, and then chain on a derivative. So that's the format for the first one. I've differentiated the outer function log base 7. Then we take 7t minus 4 and plug them in. It goes in both here and here. So that's how the middle term goes. The last term is really just rinse and repeat with slightly different numbers. Caleb says, so why are those two chain rules, but not the first one? By the first one, do you mean this right here, log base 7 of t? Or do you mean the original one at the very start? Oh, gotcha. The reason that this one, the log base 7t, is not chain rule is because all we're really doing is changing that a right here to a 7, and changing that x to a t, and then plugging in the results over here as well to a 7 excuse me, to a t right here for x and a 7 for natural log a. But here's a different point of view. Suppose you did use the chain rule on it. It actually still works. That would be the outer function, t would be the inner function, and you would multiply by the derivative of t. But it just so happens that because it's t and nothing else, the derivative of t is a 1. So you'd be plugging a 1 right here, which means no change. We can neglect the chain rule. The reason we have to use a chain rule here is because the input variable is not just t, it's something else, 7t minus 4. The derivative of all that is 7, which means if we didn't use a chain rule, we're off by a factor of 7. So if it's just a variable t, we can neglect the chain rule on these kind of problems, is the short to the story of that one. Does that make sense for that question there? Awesome. So last one, we're going to go -3, constant multiple rule. Multiply it by the derivative of log base 7, which is 1 over a placeholder like before, times the natural log of 7. Chain on our next derivative. Then with those placeholders set, plug in t power 5 plus 3 in both positions. And at this stage, we're nearly there. We're nearly out of time too, so that looks like it's timing pretty well. We just have 2 more derivatives to take into account, simplify the function, and we're on our way. So here's the next line, z prime is, well, let me remove that times there. We just get 1 over t natural log 7 on the first term plus, on this one over here, we can rewrite this as 2 7t minus 4 times natural log 7. When we differentiate 7t minus 4, all we get is 7 on that one. Then -3 times the group, t power 5 plus 3 times natural log 7. This derivative is also not so bad. Power rule on the first term will give us 5 times t power 4. And the constant will go to 0 upon differentiating. So that's our derivative. And this is kind of painful, but it's usually not left in this format. In its most simplified form, we would say z prime is 1 over t natural log 7 plus 7 over 2 times 7t minus 4 natural log 7 minus, and here's the painful step, it was just a small simplification, 15 t power 4 divided by t power 5 plus 3 times natural log 7. And finally, we've gotten it. This is the full derivative. We used the chain rule twice, but the major thing we did was properties of logarithms. And even though it looks like a lot of steps on this one, take out a clean dozen sheet of papers practically and try doing this from scratch. It's still a chain rule because there's something inside log base 7. Then you differentiate where the red dot is, but that's a quotient rule. So once you do the quotient rule on that, you'll have to differentiate the numerator, but that's a product rule. And when you do the product rule, you have to differentiate root 7t minus 4, but that's a chain rule. And you'll also have to differentiate t power 5 plus 3 cubed. That's another chain rule. It's a gigantic mess. The algebra really explodes on this one. But if you took all those steps and simplified way, way down, it's just that. One thing you'll never have to do for this kind of problem is you don't have to add up the fractions. There's no need to find least common denominator and put this under a common denominator. But this is like 2% of the work you would do differentiating that from scratch. And it's not an exaggeration. It's really hard to do this one from scratch. A good challenge problem, say at the end of the class, just to review everything at once with differentiation. Well, this is a good stopping point. Sorry for going right down to the last minute, but this was a longer one, it looks like. It didn't seem like it was going to take that long at first. But any last thoughts or questions at all, folks, before we call it a night? Okay, well, have a great evening, folks. On Thursday's class, we'll launch into the last kind of a smaller part of the notes and then get into section 3.7, our first big section on applications of derivatives. But have a great night, folks. I'll see you all tomorrow.